So, welcome back and welcome to the last lecture of current electricity, where we talk about a versatile instrument which is called a potentiometer. Here I am just giving you the principle of the potentiometer and the requisite circuit diagrams in full will be visible to you on this side of the screen. Okay. Now what we have is, in a potentiometer, we have a long wire of uniform area of cross section. It's normally a wire of which we make resistances. Okay. The length A to B is variable. Sometimes it is 6 meters, sometimes 8 meters, and usually it is 10 meters put on a meter long stand, and the wires, they take the to and fro kind of a shape which is visible there. A and B, this is maybe, as I have said, say 10 meters long wire. Okay. And this is subjected to a current I, which is obtained from a battery and a rheostat arrangement. Rheostat is a variable resistance, normally wire wound, and you must have seen in your lab classes. I'm not going to indulge in that. Well, we can change the resistance of the rheostat. Now, I have a cell which is connected to this rheostat, and this is the value of the terminal voltage, or the EMF of this cell is high enough. It's almost of constant terminal voltage, and this is able to put in a current I in this wire. This is positive and this is negative. So the potential drops as we go from the end A to the end B. Okay. And we can say that let the potential drop per centimeter be equal to 5 volts per centimeter. Okay. Now in the first part, as I said, we are going to compare the EMFs of two cells. Maybe they are the primary cells and this is the secondary cell. Okay. This is an accumulator. Okay. So what I have shown here is two galvanometers, but actually there is only a single galvanometer. But to avoid the hodgepodge, I am taking, say, one source of EMF and another source of EMF. This is positive and the negative end is connected to the galvanometer of high sensitivity. That is, it has a low resistance associated with it. Now look here, the principle is very simple. This is plus and this is also plus. Okay. And this is minus at N1 and this side also is minus. If the potential difference between A to N1 is equal to the EMF of the cell that is there, then there is no current which is passing through this part. That is, the potentiometer is the device which does not draw any current when the null point is obtained. In that condition, hardly any current is drawn by the drawn from this cell marked E1. And similarly, in the second instance, we avoid this and rather we take this path, and this E2 is also balanced at a point N2 with a length L2 associated and measured from this end. Like L1, this is also measured from this end. So we get two lengths, L1 and L2, right? And the voltage AN1 is equal to L1 into 5 volts, and voltage AN2 is L2 into 5 volts. So simply I can say that this divided by this, E1 upon E2 is equal to L1 5 divided by L2 5. So this is L1 upon L2. Okay. So the ratio of the two cells is equal to the ratio of these lengths which have been obtained under the condition that no current is drawn from the sources by the system. Okay. And whatever current initially was there, the same current will pass through it because of the arrangement which I have shown separately in order that you understand it clearly. Okay. Just to avoid that hodgepodge at the circuit, I have done that. Now, if suppose my E2, this one, is a standard cell. A standard cell is normally a cadmium cell from which you can hardly draw any current. But the potential difference, the terminal voltage of that cell is constant. Okay, so that is a standard cell. So if one of the cells is standard, I can find the EMF of cell number 1 as L1 upon L2 multiplied by E2 by the same set of formulas. So this is one of the applications in which you can compare, and also you can determine, in case you use a standard cell at a given temperature of laboratory temperature, you can that EMF is calculated, it's there. Okay. Now I have the second part where we determine the internal resistance of a cell. So I have this cell E with the internal resistance R in series with it. It's of course very small, and we are supposed to determine that. Okay. This part is connected to A, and the other end through the galvanometer, it determines when key K is open. This key is open. Okay. So naturally the resistance between this and this, that becomes infinite. So whatever is there is due to E and R combination over there. So I get the value of E as equal to 5 into L1. Okay. When the key is closed, then V becomes equal to the terminal voltage that we obtain, that becomes equal to 5 into L2. So E upon V, I get it, phi and phi cancels, L1 upon L2. But you can see that E is equal to this I, R, small r plus R. Okay, and V is equal to IR. If so, then I can find that R upon R, R plus R upon R, this E upon V comes out to be equal to L1 upon L2. Okay, and so I can find it dividing by R I get 1 plus small r upon capital R is equal to L1 upon L2. So small r can be obtained therefore like this as capital R L1 upon L2 minus 1. The beauty is that the potentiometer is functioning on the very principle that no current is drawn over there. So these are the two things, and we may return with a few numericals to wind up this chapter. Okay, those actual diagrams, they appear on this side, so please look into that and use this thing to obtain the two relations that we have obtained. In fact, we have done 3. It is also determination of an EMF of a cell in case a standard cell is used. Okay, so there is a very simple exercise concerning a potentiometer. The wire is between A and C. Okay, and this resistance of the potentiometer is equal to R naught plus R naught. That is 2R naught. Okay, and we connect another resistance capital R from A to the point B, which is midway between, if it is 10 meters, then it's 500 meters, 5 meters, etc. Doesn't matter. So this has been shown. Now, what I have shown here is cross feed. Okay, it shows that this is connected to the positive terminal of a battery arrangement, and this is grounded, so this comes here. Okay. This is also a way to show, that's why I introduced it for you. The potentiometer resistance is equal to 2R2, capital V is the power supply, and now what is desired of us is to calculate the value of the drop across the points A and B, which is VR. Okay, this also I can say this is VA to B. It can be also asked like that, so don't get confused, both of them are the same things. Okay, now look here, this is now a parallel arrangement of two resistances R0 and R in series with another resistance R0. This is a very simple thing. Okay. So I can say that the resistance between the points A and B, that is the parallel combination of R0 and R, so it turns out to be R0 R upon R0 plus R. Okay, and the current which passes through it, which I have shown deliberately over here, because some part of this current will flow through this part and some will flow this way, and then from here to here it will become equal to I. So the current is equal to the power supply voltage V divided by the parallel combination resistance plus R0 this resistance. This is the resistance between the points A and C. Okay. So therefore we can write VR, they are VAB, whatever you want to say here, VAB again we can write between the points VAB. Okay. This will be equal to the total resistance over here multiplied with current R. So this I write like this, plus for current I put this over here, just a mere substitution. Okay, so there is this in the numerator and this is in the denominator. Okay, now I divide the numerator and denominator by this quantity, so I get like this, like a child I have done. So this is R0 R upon R0 plus R divided by R0 R upon R0 plus R. Okay, so this will turn out to be equal to 1 plus R0 divided by this quantity R0 R upon R0 plus R. So R0 this and R0 this will cancel out, this will go, in the numerator and this will remain in denominator. So this becomes equal to capital V divided by 1 plus R naught plus R divided by R. And you can see that if I multiply here by R, right, so I'll get R naught over here, R over here plus R naught plus R, and this R will go up. So the value becomes equal to VR divided by R naught plus 2R. So this is a very simple exercise that I have done, and you can say that similarly it can be changed 3/4 this side and 1/4 this side, etc., etc. That kind of variation can be done. Okay, so now to top it all, I have just taken a few arrangements, okay, and how to solve them, what are they, because this appears to be a different topology, okay, and creates confusion. To remove that confusion, I have these three resistances R1, R3 and R4, okay, and point A and C we have a resistance R2, and between B and D there is a resistance R5. Now I am just drawing it again in the form of a Wheatstone's bridge, okay. So A to B there is R1, and B to C there is R3, and C to D there is R4, okay. R2 is between A and C, and R5 is between B and D. Okay. So naturally now this becomes a kind of a Wheatstone's bridge arrangement, and if they say that the potential at point B and the potential at point C is the same, okay, we can see that R1 upon R2 is equal to R5 upon R4, then of course this is the balanced bridge, and that way we can solve the problem. Okay. Number 2, there is a zigzag kind of arrangement of resistances like this, and there are 4 loops like that. So what we can do is we just look into it and solve it readily within seconds. Okay, I've just shown these points. Now look here, there are 2 resistances in series and 2 resistances again in series, and like this same way this is repeated. Okay, 4 sets are in series with each other. Now the resistance R plus R is equal to 2R over here, and 2R plus 2R is equal to 4R over here, which I have taken and shown you here as 2R and 4R, and then the net resistance will be equal to 2R into 4R divided by 2 plus 4R, which is 8 upon 6R, which is 4 by 3R, multiplied by 4, and you get readily the value to be 16R by 3. R can be given any numerical values also, there is no problem. Okay. Now here is the ladder network. Okay, I have shown a typical ladder only, but other kind of ladders can come, and how we solve this problem. So look here, we have to measure the equivalent resistance between these 2 terminals, and this kind of arrangement repeats itself again and again, and we say ad infinitum, so it is up to the infinity. So what we do to solve such a problem? Okay, when we look into it from this side, then we find that the resistance over here is R equivalent. Okay, now look here, friends, that if instead I look from here, then again the same thing comes, and the total resistance beyond this is equal to again R equivalent. So I can now make it R equivalent for the rest of it, and then my R and R, this we are taking everything as it was. Now we solve for the R equivalent. R equivalent turns out to be the parallel combination of these 2 resistances plus series combination of this and this and this. So I'm writing R equivalent as R is equal to R equivalent upon R plus R equivalent plus R, and of course that is 2R plus this, and then we multiply it and we get a quadratic equation. Okay, ax square plus bx plus c type. Okay, and so we solve it for x as equal to minus b plus minus under root of b square minus 4ac divided by 2a, that kind of a thing. And I hope that you are competent enough to do that. So I'm just giving you a hint how these kind of problems are solved. Friends, what we can do is we can keep capacitors also over here. Okay, some values of capacitors. Similar values will come over here, and I told you in case of capacitors that this kind of arrangement can be done. Similarly, these capacitors, if they are capacitors, then R plus R will become equal to R by 2. 2R, I'm sorry. C and C will become in series C by 2, and here 2C, 2C, C, etc. And we can then solve like that. Bear in mind that the capacitors in parallel have a different formula than the resistors in parallel and in series, etc., etc. Here also I can keep capacitors and we can make solutions. Of course, another thing which we can do is that we can, instead of putting the R, we can put the impedances and again look into it and solve like that. So this is the kind of tarkeeb, the way that we attempt these questions, and we can solve them readily. Okay, with a little bit of practice you can do it in a minute's time. So it was a pleasure to be talking to you about current electricity, many more aspects, but of course I cannot touch upon all those aspects. Advanced aspects are there. We will now advance to magnetic effects of current. Okay, and I expect you may not follow what I request you, that our aim is to answer your questions, and our aim is that you raise questions. Okay, so please ask questions. If you have any problems other than these things, just you can send in the comment section, and we'll try to be honest. If we can answer, if you are asking questions relating to physics and doing physics, we'll answer that. So see you soon for the new chapter.